I'm a PhD climatologist, climate researcher for over 25 years, and so I can tell you a bit about how the climate has changed where you are physically right now in Banff, and talk a bit about how our most recent science is telling us about how it's going to change further under climate change. Dr. Adam Fenech's not the only person who says this. The Intergovernmental Panel on Climate Change as well says that if you need to or want to look at the vulnerability of your sector or your location to climate change, or you want to look at the impacts or how you're going to adapt, the very first thing you have to do is look at the past climate and then look at the future climate, because this gives you the fundamental background for how you have been impacted in the past, how you've adapted in the past, and what the frequency and magnitude of the extreme climate is going to change into the future, to give you an idea of the magnitude of changes that are being forecasted. And I'm going to suggest to you that all of the trends that we're looking at here, I'm going to look specifically at the climate record that comes from Banff, Alberta. However, these are indicative of other climate studies I've done in Alberta, so the trends are going in the same direction. And I'll tell you that they're also in the same direction that we're seeing in Ontario, as well as throughout the Atlantic provinces. So we are undergoing some changes in our climate. Overall, we can say that over the last 125 years that Banff's temperatures have been going up, and this is indicative of all of the other Alberta stations that I've looked at, and like I said, other parts of the world. And the way that we read this slide is that running along the bottom are the years. So it's 1888 are when our records start, and going all the way over to 2012. The one that you see on the graph is 2011. And each year you can see, and this is the annual mean temperature in degrees Celsius. And you can see that year to year there's some quite variation. You know, it goes up and goes quite low, the average temperature. But overall, that trend is increasing. And the way that climatologists look at climate is that we talk about climate normals, and that's usually a 30-year time period, and that's how we consider climate. The climate normal, whenever you hear things such as it's warmer than normal or colder than normal, there's just more snow than normal, climatologists are talking about a 30-year period that has just occurred. So currently our climate normal that we're looking at is 1981 to 2010. And that's what's at the end of our graph we're showing here. And if we take these 30-year segments, these climate normal, it's like a moving window. You can see that we're currently in, or just past, a climate normal period that's been warmer than any that we've seen over the last 110 years or so. The temperatures themselves, what you're looking at here, again, we're looking at 1888 going across to the year 2012. And it's in degrees Celsius. The top line is, of course, the maximum temperatures for each year on average. And then the middle is the annual mean temperature that you've seen already. And the lower one are the minimum temperatures. And you can see that most of the increase that's occurring, that's driving up this annual average temperature, is happening in the minimum temperatures. And that means that most of this is happening during nighttime lows. They're no longer as cold as they used to be. And this is not something that's just happening in Banff or just happening in Alberta. It's happening in Ontario and in the Atlantic provinces, and in fact, it's happening all around the world. So a lot of climate change in terms of these average temperatures increasing is happening while we're probably asleep. Seasonally, most of those increases, the majority of it is coming from winter. You can see that all of the seasons, here we're looking at seasons going across from 1888 to 2012, they're all increasing, but the one that's increasing the most are the winter. So it's the winter nighttime lows that are really driving the whole process, which may or may not have implications for agriculture. One way of looking at this as well is because we have such a nice long record at Banff, Alberta, and I must commend Lucy Vincent from Environment Canada, who gave me access to what we call a homogenized temperature data set, because it's allowed me to look this far into the past, because I don't think such a long record is available publicly. But if we look at temperatures, this climate normal period that I talked about, in this case we have to go from 1988 to 2012 and compare it 100 years earlier. You can see that every single month out of the year is warmer except for December. Okay, so if we went back in time and we're living in Banff, every month out of the year would be colder except for the month of December. Now, I've looked into the records for why is it December that's such an anomaly here, and I haven't been able to figure it out. But it's at least verified. I've been able to look through the data sets. But you can see that every single month is warmer than it was 100 years ago except for December. As we move to extreme hot days, now I define extreme hot days as those days where the maximum temperature is greater than 27.5 degrees Celsius. Now, I get that number from Occupational Health Canada. It's an organization in Ottawa that provides guidelines for provinces. If you have outdoor workers, then if the temperature is above 27.5 degrees Celsius, they recommend that you give your outdoor workers a break every hour because it's going to impact on their human health. I just find it as a nice threshold to use and as a way of comparing all across the country, a similar threshold. And you can see in the left-hand bar graph there that from 1888 to 2012, you have this very steady increase in the number of extreme hot days that have occurred in Banff, Alberta. So these are days above 27.5 degrees Celsius. Now, there's some years where you don't even get any that are of that warmth, but there's certainly some the frequency or the year with the most extreme hot days occurred. It looks like there to be about 2003. So in a really recent period. Looking into the lower right-hand corner, if we look at 100 years later again, if we take that time period of 1888 to 1912 and compare it 100 years later to 1988 to 2012, it gives you a sense of the magnitude of the change that we're talking about. So once again, if we went back 100 years in a time machine, we'd see that things were not as extremely hot as they are at this time. Next slide looks at extreme cold days. And again, these are, I'm explaining, or I'm using these indicators, and you as farmers or looking at agriculture can certainly understand their implications to the work that you do if these trends are occurring. In this case, the extreme cold days are those days where the minimum temperatures get below minus 20 degrees Celsius. So once again, this is a threshold given to me by Occupational Health Canada, in which outdoor workers, if the temperature drops below that value, they recommend that outside workers get a break every hour. So you can see that in the left-hand graph that going from 1888 to 2012, once again, there is this downward trend in the number of days, extreme days. There's still years in which there's more than others, and in fact, even recently, it looks like about 1996, there've been quite a year where there was a significant number of extreme cold days. So those we still anticipate under changes that are going on. When we look into the lower right-hand corner, this is that 100 years later again. So comparing two time frames, we during that climate normal period of 1888 to 1912, that there was a sum of 33 extreme cold days, on average, has gone down to 21. Well, that was the temperature. So I'm going to talk to you a bit about the precipitation, the snow and the rain. Things have gotten slightly drier. Here there are gaps in the records that I've been unable to, do our magic to fill. But again, we're looking at a time period here of 1894 coming across to 2013, and but it gives you an idea that there really hasn't been that much of a change, but it has, especially over the last few years, been a little drier than we expect, than what the average trends were. We're going to look at the climate normals again, and so these are those 30-year periods that is a moving window and gives us an idea of sort of the slow changes in climate. And you can see at the far right-hand side of the graph with the bar there that we're at a climate normal from 1981 to 2010 is at 477 millimeters per year. Now, it's certainly the driest period that we've seen in terms of climate normals in a while, but not as dry as a time period that occurred in the 1920s and 30s. Overall trend based on season, and this is based on a percentage change. And so anything above the zero line means that things have been getting wetter, and anything below means that any negative numbers show that things have been getting drier. And so you can see over that long time period that the summer, autumn, and winter have been getting drier, and the spring has been getting wetter. Now, that's a long period of time to look at. We normally would want to look at the last 30 years to see where the trends have been emerging recently, and that's something we should take a peek at. Now let's look into the future. Okay, now the way that we do that as climatologists is we have these global climate models, and these global climate models are simply mathematical equations that try to represent how the atmosphere, the physics and chemistry of the atmosphere, so it's the basic laws of physics and chemistry, so there's nothing magical about them, and try to link that up with the ocean influences of climate and the land influences of climate. Now, these mathematical equations take a long time to run. They take the largest computers in the country to run them. We call them supercomputers, and supercomputers are what forecast our weather, and they're also used to give these long-term projections of global climate as well. The advancement in the computer technology since I've been involved is quite significant. When I started back in 1987, we were dealing with a Cray computer that was about the size of a small room. And this was the largest computer in the country that was forecasting our weather and running these global climate models. Now, I'm told the same type of capacity of that computer that was the size of a room is what we carry around in our pockets as our smartphones nowadays. So it's hard to even imagine 25 years from now where the computer technology is going to be able to take us in terms of doing these types of modeling and predictions. So let's go to the next slide and then give you an idea of where our latest science is telling us. Well, little old University of Prince Edward Island is the only place in the world, and I'll say that again, the only place in the world, where we have output from the 40 global climate models used in the most recent IPCC assessment reports. Now, those reports are just being released. One was released on the weekend, another one's coming out early April, one was released last October. But the output from the global climate models that's used in those assessment reports has been available through the IPCC Data Distribution Center for over a year, maybe even a bit longer. But we've taken the time here at the university to download all of the output from the models and put it in a form that's easily mappable and easily analyzed. So if you need some of the most advanced science on future climate modeling, then we're one of the places to go. The only place right now if you want all 40 models used. And using a baseline of the most recent climate normal period of 1981 to 2010, this is what the temperature change is projected to be. This is using a mid-greenhouse gas scenario. The largest uncertainty in global climate models is that we don't know what the greenhouse gas emissions are going to be like in 50 or 70 years from now. I mean, we can guess at what they're going to be or give some educated estimates, but what drives the greenhouse gas emission scenarios are the number of humans on the planet. And if you ask, you put 100 experts in a room, they'll give you 100 answers for how many humans we're going to have in 60 years. And we'll have a good range, and that's what we put into the models. The second is the type of energy use that we have. We seem to want to burn every fossil fuel that we can find, but there is a movement towards more renewable energy, but we just don't know in 50 years where we're going to be in terms of how much renewable energy is going to be making up our energy mix. The third is the type of economy. A well-integrated economy is really good at alleviating poverty, but it's not very good for the environment. So all it would take is a significant outbreak of war somewhere in which it would lower our economic activity, and shipping of goods and services around the world would therefore reduce our greenhouse gas emission scenarios. So I've been cautious here and just taken a middle ground. So we're using the mid-greenhouse gas emission scenario. We call it RCP6. You don't need to know why. And what that says for Alberta is that we anticipate by the 2050s that there will be a change. And since all these numbers are positive, that means an increase in the annual mean temperature of about 2 degrees Celsius. Okay, and I'll show you a bit about what that means for implications for agriculture soon. But here's a graph that you can always go back to when you're thinking about, well, what are the implications for the region? Next slide will show what the precipitation change is. So again, under that same mid-greenhouse gas emission scenario, with a baseline of 1981 to 2010, and this is in percentage change, and since these are positive numbers, it's anticipating that there will be a 3 to 4% increase in precipitation, which kind of goes against the trend that is happening towards drier. But that's similar across the country as well. Next slide, we'll talk a little bit about the frost-free season. Okay, now this is using just one model. The previous two graphs were using what I call an ensemble of 40 models. So using all the model input to give us sort of a generalized, most likely future scenario. This one is using the Canadian Global Climate Model 3. If you look at the bar graph in the left hand of the slide, it's the number of days without frost, so the frost-free season. The 1971 to 2000 are the actual number of days, where the others are projections for the 2020s, the 2050s, and the 2080s. And so you can get a sense there of the magnitude of change that is anticipated. Next slide will take us to the growing season length. And again, this is zeroed in or focused on Banff, Alberta, specifically. As the number of days of a growing season length, this would be using an international indicator of when you have 6 days in a row of temperatures above 5 degrees Celsius, and then you have 6 in a row below 5 degrees Celsius. That sort of triggers the beginning and end of the growing season. This is, again, if we just look at the bar graph in the lower left-hand part of the slide, you can see that 71 to 2000, there was 145 growing. The growing season was 145 days, and how that increases over time as we move into the future. And it gives you a sense of the magnitude of change that we're anticipating. Banff has become warmer and drier over the past 120 years. Certainly the warmth is happening more in the minimum temperatures, the nighttime lows. The winter time is getting a little bit warmer than the summers are. The extreme hot days are definitely increasing, and extreme cold days are decreasing. The future temperatures are projected to be warmer, about 2 degrees Celsius for Alberta, and wetter, about 3 to 4%, and this is by the 2050s. The frost-free season is seen by increasing by 28% by the 2050s, and the growing season length increasing 19% by the 2050s.
Hey, Adam. So when I was listening to your presentation, what I was seeing was basically an increase in temperature and an increase in precipitation, which to me makes sense because your evapotranspiration would be increased with the increase in temperature, which would allow for more water to be in the atmosphere for rainfall. One of my questions to you, though, is with all this assessment that you have been doing, have you looked at the duration and frequency of the precipitation and drought events that could occur as a result of these changes?
I think the question was, have I seen and have I studied the changes in frequencies of drought? Was that the question?
Yeah, because if you have an increase in precipitation overall, it's a little deceiving if your drought periods are extended. So instead of having periodic droughts throughout the season, if you have a 3-month drought, that's going to have a significant impact on your agriculture and tree growth, as opposed to periodic droughts throughout the year, but may not change your annual trends on your precipitation factors.
Yes, I have not specifically for Banff, but I'll tell you the conclusions that I found at every other place I've looked at. There are 2 indicators that climatologists look at that are try to answer the question that you're talking about. One is, it's called precipitation frequency, which is the number of days that actually receive precipitation. And there's something called precipitation intensity, or how hard is it raining or snowing. And with every location across the country that I've looked at, the frequency is decreasing. So the actual number of days with precipitation is decreasing. But the actual intensity, or how hard it's raining or snowing, is increasing. So for example, I was just on the radio yesterday talking about our winter here in Prince Edward Island, where we haven't seen it for similar snowfall for 42 years. But there was a totally different type of winter. Back in 1972, we had 90 days of snowfall, where here we've only had 47 this current year. And back in 1972, up until the end of March, they had not had any snowstorms above 25 centimeters, where here during this year we've had 4 of those. So it's this whole idea of more intensive, less frequent precipitation events. And what that does is it stretches out the number of days that you could go without precipitation. So hence the drought that you're talking about. And also, it's here on the island, at least, it's also led to certain flooding events during the springtime, because you get that intensive rainfall rather than the rainfall spread out over a period of time. But I have not looked at it specifically for Banff, but that's what I'm finding in virtually everywhere else I've looked across the country.